Kinematics is going to be our first unit of study this year. And in kinematics, we're looking at how things move, not why they move. We're interested in the motion of the object. This is something that we can see. All right. Now, why things move is not something we can see, and other aspects of the motion of the object are things that we really can't see. We can talk about them, some of it we can measure, and I'm referring to things like force. You can't see a force. You can't see energy. You can't see momentum. So kinematics is only interested in those things that we can see. As a car is driving down the road, you can see if it's moving left or right, speeding up or slowing down. How far did it go? Those are things that kinematics deals with. Now, before we can have a meaningful discussion about kinematics, we first have to talk about vectors and scalars. A scalar quantity is basically, it's just a number. It tells you how big something is, and that's all it does. So examples of scalar numbers would be to say 3 feet or 30 degrees Fahrenheit or Celsius, 10 oranges. All right, these are all things that have no direction associated with them. Scalars are pretty easy to work with. We like to work with scalars. But unfortunately in physics, many of the values that we have to work with are vectors. Now, a vector quantity is a quantity that not only gives you the magnitude, but it's magnitude plus direction. So, for example, you might say 3 feet to the left, 10 miles per hour north, or even 70 meters southeast. Okay, all three of those values are vector quantities because they tell us how big and in what direction. Now, when we represent a variable which is a vector, for example, velocity is a vector, we would write v for velocity. So that we know we're dealing with a vector, we're going to put the vector symbol over top, which is basically just an arrow or a half arrow. So this would be a full arrow, and that's how some people draw it. You could do it like this, where it's just a half arrow. Either way is acceptable. Now here's the thing though. While we do this as a formality, in practice we're not going to be writing these vector symbols over top of our variables as we solve problems. Now there are a couple different ways of representing vectors. Vectors can be represented numerically, and then they can be represented graphically. We're going to take a look at the numerical representation first. So when we're working in one dimension, there are only two possible directions something can move. It can move left or right, it can move up or down, it can move in or out. Sometimes we'll talk about it as being north, south, east, or west. But it's only two possible directions. So in math, we distinguish the difference between up and down, left and right, in and out by using positive and negative. There are no hard rules on what is positive and what is negative. We have what we call a sign convention. And you may choose to deviate from the sign convention and do something that is not this. But that's not allowed in my class. Technically it is allowed, but in my classroom I do not allow it because you're too new to doing physics and dealing with vectors, and it creates a lot of confusion for many students. So the sign convention is this. Any quantity which is positive is one which is moving up or to the right, north or east. Any quantity which is negative will be the opposite of that. So it's going to be down, to the left, south, or west. So let me give you an example of the usage here. So for example, we set up above 3 feet left. Well, 3 feet left would just be written as a negative 3 feet. If I said 100 miles north, then I would just write 100 miles. If you want to make sure that it's perfectly clear that it's a vector we're dealing with and not a scalar quantity, you could put the plus sign out in front of it. And if I had 50 miles per hour to the west, then I would just write minus 50 miles per hour. So the plus and minus sign indicates, which way it's going. This is really useful for when we're adding or multiplying our vectors. So if we're going to add vectors, and we'll deal with this in much greater detail as we go throughout the course. But if we're going to add vectors, let's suppose I have vector 1 is displacement 1, and we'll say that that's minus 10 meters. Vector 2 is displacement 2, and we'll say that that is 25 meters. Because there's no plus sign, or I should say because there's no negative sign, it is assumed to be a positive direction. So that if this were left and right motion confined to the left and right direction, then the 25 meters would be to the right and the minus 10 meters would be to the left. If this happened to be for vertical motion, then 25 meters would be up and the minus 10 meters would be down. So if I want to find the total displacement, d total is just equal to d1 plus d2, which is minus 10 plus 25, or plus 15 meters. And again, if we're saying that we're moving left and right, then this is going to be 15 meters to the right. But the fact that it's positive tells me that it's going to be to the right, and I don't need to actually write that out. Now, it doesn't matter which direction you add or what order you add vectors in. We could do d1 plus d2, or we could do d2 plus d1. So that would be 25 plus a negative 10, which is still 15 meters. Now, in the graphical representation, arrows represent the vector. Which, by the way, is the reason why we could put that little vector symbol that is an arrow over top of every one of our vectors. Like I said, in practice, we don't do this as we're solving problems, but it's assumed to be there. We understand that when we're talking about a displacement that it is a vector. So we write it out formally, but we don't have to. Anyways, we represent vectors by using arrows, and the size of the arrow or the length of the arrow indicates the magnitude. And the head of the arrow indicates the direction. Now, the thing about this is you must set a scale. So when you're drawing these out, you have to decide, does 1 inch represent 10 newtons? Does 1 inch represent 100 newtons? Etc. Again, in practice, we don't typically use the graphical method when we're trying to determine numerical values for a problem or a situation. The real strength of a graph, or the graphical method of vector addition, is that it gives you a visual on what's happening within the problem, so that you can anticipate, should my answer be large or small, or maybe something in the middle? Is the direction possibly or probably to the left or to the right? Things like that. So that's the real strength of representing vectors graphically. When we represent vectors graphically, we use what we call the head-to-tail method. In the head-to-tail method, this is what you're going to do. You're just going to take one of your vectors and you're going to place it anywhere on your page. It doesn't matter where, because vectors don't really have a home, a starting point in the problem. You can draw a vector anywhere you want to draw it, relative to your coordinate system at least. Then what you're going to do is you're going to place the tail of the second vector on the head of the first. The resultant, I'll talk about that in a second, but the resultant goes from the starting point to the ending point. So what that means is this. If we go back to, we have vector d1 and d2. If I want to do vector d1 plus d2 in order to get d total, then I'm going to place one of those vectors. And let's say I start with vector d1. Why not? We'll just do d1 plus d2. Then d1 is to the left by 10 units. I don't know what that looks like, and I want to make it fit on my page, so I'm going to say 10 units is this. This is vector d1. Vector d2 gets added head to tail. So I take the tail of vector 2, and vector 2 is going to point to the right by 25. So vector 2 is going to go head to tail. Now, technically I should draw this right over top of that arrow, but I'm going to put it a little bit below so we can see it. And I'm going to come back in this direction. There's 10 units. Here's another 10 units, and then I got to go 5 units past that. So this is vector d2. Now remember, this was 10 meters in length, and this one is 25 meters in length. So our resultant is this. From the starting point, which is right here, to our ending point, which is right here. And the resultant is going to be plus 15 meters. The order in which you add these vectors does not matter. Just like in the addition up here, the order didn't matter, the order down here doesn't matter either. So you could do d2 plus d1, and if we just sketch it out real quick, here's d2 plus d1, and that's still going to give us this vector that points to the right, our resultant vector. Now, the last thing I want to say about our resultant vector is this term resultant. This is a generic term. And we use it whenever we don't have a context, or maybe we want to specify that a vector quantity is the end result of doing some addition. Sometimes we'll call that the resultant. So the resultant displacement, for example. I'm calling it d total. D total is the resultant displacement. So anyways, it's a generic term. And what that means in practice is that it represents any vector. It doesn't matter. It could be force, acceleration, momentum. It doesn't matter. So it just represents any vector or the result of adding up multiple vectors. But those vectors are going to have to be of the same quantity. So you d1 and d2, they have to be, in meters. You couldn't add 3 meters plus 25 meters per second. you're adding displacement and speed. And, well, that just doesn't make any sense. That's like trying to say I've got 3 apples plus 2 oranges should be equal to 5 apples. Well, that doesn't work. 5 oranges? No, that doesn't work either. You could say 5 pieces of fruit, but that's not exactly what we're doing here.